Welcome. Today we're diving into input-output optimization techniques. This is all about how we can reduce disk input-output to achieve better performance in our systems. Let's explore the strategies that make our applications run faster and more efficiently. First, let's understand the common performance issues related to input-output. Disk access is significantly slower than memory access. Random input-output operations are more expensive than sequential ones. Excessive read or write operations can cause system bottlenecks. Inefficient buffer management increases latency. Synchronous input-output blocks program execution. The diagram illustrates the input-output stack, showing how data moves from the application layer through the operating system and buffer or cache layer before finally reaching the physical disk storage. Now let's look at buffering techniques. First is buffer caching. Buffer caching keeps frequently accessed data in memory to reduce physical disk access. The operating system maintains a cache of recently used disk blocks to improve read performance. Here's a simplified buffer cache implementation using code. Next is double buffering. Double buffering uses two buffers to allow simultaneous input-output operations and processing. While one buffer is being processed, the other can be filled with new data from the disk. Here's an example of double buffering using code. Next, let's discuss input-output scheduling techniques. We have disk scheduling algorithms, which determine the order in which disk input-output requests are serviced to minimize seek time and maximize throughput. In the code snippet, we have first-come, first-served, or FCFS scheduling algorithm. Then we have scan or elevator algorithm. The disk arm moves in one direction, servicing requests until it reaches the end, then reverses direction. This reduces seek time and prevents starvation. The diagram shows how the disk arm moves from track 0 to track 199. Here is the sample code to demonstrate the disk arm movement. Now we will explore asynchronous input-output in input-output parallelism. Asynchronous input-output allows a process to continue execution while input-output operations are in progress, rather than waiting for them to complete. As you can see in the diagram, synchronous input-output blocks process until input-output completes. On the other hand, asynchronous input-output process continues execution. The code shows how to use a synchronous read and continue execution without waiting. Next is input-output parallelism. It means performing multiple input-output operations simultaneously, using techniques like RAID or redundant array of independent disks to distribute data across multiple disks. The code shows how to perform parallel reads from multiple disks. Here we will discuss read-ahead and prefetching. First, we have read-ahead buffering. It anticipates future read requests by loading additional data blocks into memory beyond what was immediately requested, reducing the number of disk accesses. As you can see in the diagram, the current block is currently in use and blocks 2 and 3 are prefetched, while blocks 4 and 5 are not loaded. There is also a legend. Second, we have adaptive prefetching. Adaptive prefetching dynamically adjusts the amount of data prefetched based on access patterns. It increases prefetch size for sequential access and reduces it for random access. The code example shows the adaptive prefetching algorithm. Now we will discuss write optimization techniques. The first technique is write buffering, which accumulates multiple write operations in memory before committing them to disk, reducing the number of physical input-output operations. In this way, multiple write operations is performed on memory buffer, and then single input-output operation is performed on the disk. The code example shows this buffered write method. The second technique is write coalescing, which combines multiple write operations to adjacent disk locations into a single larger write operation, reducing seek time and improving throughput. The code example shows how to coalesce the writes. To summarize, buffering techniques like buffer caching, double buffering, and write buffering are used. Input-output scheduling algorithms such as the scan or elevator algorithm minimizes seek time. Asynchronous input-output prevents blocking execution, and input-output parallelism distributes operations across devices. Read-ahead prefetching anticipates future requests. Write coalescing combines adjacent write operations, and adaptive algorithms adjust based on access patterns. Some best practices for input-output optimization are: minimize random access patterns when possible, use appropriate buffer sizes for your workload, implement asynchronous input-output for non-blocking operations, batch small input-output operations into larger chunks, monitor and profile input-output performance regularly, consider hardware solutions, such as solid-state drives and RAID for critical workloads. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.